When we learn about statics, most of our time is spent dealing with what we consider external forces. Let me show you some examples of external forces. Let's say we have a truss, and what we mean by external forces are all of the applied loads that are externally applied to our structure. So maybe someone's pushing down on it here, maybe someone's pushing down on it over here. Those blue forces are our externally applied loads. We also dealt with reaction forces. Let's say it had a roller over here on the right and a pin on the left. Reaction forces may have been two vertical forces and a horizontal force we needed to solve for. These are all externally applied loads that have been applied to our truss. And the statics procedure for solving is we would use summation of all the forces in the X have to add to zero, all of the Y forces have to add to zero, and the moments about any point also have to sum to zero. And we would use these three equations to solve for unknown, usually the reaction forces. So we're solving for unknown external forces. And in statics, we get so much practice with this. We do it for trusses and frames and machines and rigid bodies and particles, where we find all of the externally applied loads, we solve for the ones that we don't know. Well, today we are going to dive into the concept of internal forces. You have seen internal forces in statics before, but only for trusses. So we did it two ways. One was by taking a section cut. So let's say I want to know the force in some of these members of my truss. I can take a section cut like that, and I'll draw my purple section cut, where what I need to do is take everything left or right of the cut. I need to include on this free body diagram all of the applied loads that apply to that part that I'm keeping. So I'm cutting through this dashed purple line and keeping everything to the left, including the loads. So I would still have my blue and green external forces on there. But now, because I have cut open these three truss members, I've removed something. We remove a support from an object while drawing a free body diagram, we replace that support with what it does to the thing we're drawing. So because I've chopped off these parts of these members, which were contacting the other half of each of those members, they were probably doing something. In particular, they're usually pulling or pushing in tension or compression. So what we would draw on our section cut is a force here, a force there, and a force there. Those are what we call internal forces. Okay, and you've used those before in statics. You've seen those internal forces in a truss when you cut open a section. You've also seen those internal forces in trusses when you did a joint diagram. So let's say I take that joint right there and I want to do a joint diagram. Here is my joint, and it still has an external force applied to it, the blue downward force. But now on that joint diagram, I've basically, either you can think of it as you've removed those three members or you've cut them open. And what they end up doing is applying tension or compression to that joint. Those orange ones are also internal forces. So we've seen internal forces before, but only in a limited case. Specifically, we've only seen them for trusses. In a truss, everything is a two-force member. And I don't know how well you did with two-force members in statics, but here's a really quick refresher. If I have a member AB, all it has applied to it are forces at its endpoints. The only direction that force can possibly act for it to be in equilibrium is aligned with member AB, in this case, in the X direction. So when I go to cut this member open, I'm going to cut it right here, and I want to draw a free body diagram of one side or the other of a two-force member, I like to draw those cuts a little bit jagged. It helps reinforce that this location right here is where I have cut it open. I'm drawing this part again, cut open at that green cut. Well, at end A, I still have my external force in AB. At the cut, well, what I'm going to have for this to be in equilibrium is to the right, FAB. Well, that is actually, as an internal force, it's going to be given a letter N, and it's going to be called an internal normal force. Okay, normal just means perpendicular. The reason we call it the normal force is because our cut face here is vertical. This force is perpendicular to it, so it is our internal normal force. And we used a sign convention when we did this, that positive was tension and negative was compression. And we're going to keep this sign convention and use it even for things that are more complicated than trusses. When we go to find the internal force, if it is pulling out and away from that surface, it is considered tension. So what I've just drawn on here is an example of tension. Why is it tension? It's because we're replacing the thing that we removed with its effect on the thing we're actually drawing the free body diagram of. And the thing we removed was tugging to the right on this part. This does not mean that this part was pushing to the right on the other part. We always draw in a free body diagram the loads that the other things we're not drawing apply to the thing we are drawing. So we did this with trusses already in statics. Now we got to do the more general case. The more general case looks like this. Maybe instead of a truss, I have a cantilevered beam, a beam that is fixed to the wall, and somebody is applying a downward external force of P out here. And let's give it a dimension. Let's say it has a length L. And what if I want to know the internal forces at some location? So let's come over some location and make a cut. So anytime you want to find internal forces, you're going to make a cut. This is just like what we did with trusses. To find an internal force here, we cut it open, and that enabled us to find internal forces. To find the internal forces at a joint, we basically cut with this little dashed orange line around a joint. So to find internal forces, you have to cut something apart. And before you start cutting things open, it's usually really helpful if you've already found the external reaction forces. So we're going to actually do a first step before we draw that cut free body diagram. Our first step is going to be find any external reaction forces. Let's draw a whole free body diagram. We are going to have our downward load P over here at point A. We're going to have an upward AY, possibly to the right, an AX, and potentially a couple moment MA, because a fixed support can produce a moment as well. Then we do our equilibrium equations, which we're going to do really fast today so we can jump to the new stuff. Summing forces in the X, you get AX is 0. Summing forces in the Y, you get AY equals P. And summing moments about point A, you get that MA is equal to P times L. So we've got our reaction forces. Now we're going to do, I guess that was step 2. Finally, now we're going to do our cut open free body diagrams. So when you cut these, the idea is you're chopping it right into 2. And what you're going to do is draw the free body diagram of either everything to the right or everything to the left, including all external forces. So I'm going to draw both of them so we get really good practice of this. If I keep everything to the left of the cut, P doesn't act on this part. P is all the way over here on the right. It doesn't act on this part, but all of these reactions that I just solved for do. So let me draw them on here. We already know what they are. So we'll just call that an upward P. AX was 0, and our couple moment is PL. Okay, that doesn't look like it's an equilibrium to me. So what we need to draw on here at my cut is I'm going to draw an unknown normal force out and away from your cut. I'm going to draw an unknown force parallel to the cut. And I'm going to draw an unknown internal moment, M. These guys all have names. N is called the normal force. V is called the internal shear force. And M is called the bending moment. We're going to use those names all semester. Normal should make sense. It's perpendicular to the face. Shear force is just the force that's parallel to the face. And bending moment is a moment that tends to want to make this part, bend or curve upward. Like that. That's one of our free body diagrams. I wanted to also draw the other one for practice. The other diagram has the cut on the left and we keep everything to the right. Well, in this diagram, you would draw your downward blue external force P, and then you draw the exact same things on the cut, but in the opposite direction. Your normal force has to be out and away from the cut. Shear force, if it was down on that side, it's got to be up on this side. And if your bending moment was counterclockwise on this one, it's got to be clockwise on the other face. This is just like when you did frames and machines and statics, when you took two things apart, when they were connected to each other, you always have to draw equal and opposite forces on them. And that's exactly what's happening here. I've cut this thing open, and here's one side, here's the other side of that cut. And whatever you draw on one, you got to draw exactly the opposite on the other. I mentioned tension was considered positive for normal. Well, here is our picture of all of our positive sign conventions that we're going to use in our class. There are a few textbooks out there that change the sign convention slightly, but for our class, we're always going to have V if it's down on this side and up on that side, and moments that are in this direction are what we're calling positive in our class. That's all the new material for today. Now let's do an example. Here's my first example. We've got a bar that is pinned at A. At B, it's pinned to this other member, BC, that goes back and is pinned to the wall at point C. Looks like it's got a distributed load acting on it and a downward to the right 150-pound force at a 30-degree angle. And we've got dimensions between a lot of points on here. And you'll notice this has a lot more points than the usual problem. Now, from a statics class, you would have just been asked to solve for probably the reaction forces at A and C, and that's it. So you wouldn't need points D, E, F, or G. But for this problem, we're actually going to go and find the internal forces at points D and E and F and G. And the reason we're going to do all four is because we need the practice. That is our problem to solve. We're finding internal forces. Before we start cutting anything apart, we want to first do a whole free body diagram to find any of those reaction forces. And I don't know if you noticed, maybe it's been a while since you've done these kind of problems, but this bar right here from B to C, it's a two-force member. It is only pinned to something at B and pinned to something at C with nothing else acting on it. Because of that, we know that its internal force is going to be either in tension or compression. That big, long horizontal bar is what I'm going to draw the diagram of, because when I remove this two-force member right here at point B, I will simply draw on it at point B a force in that direction. So at B, we're going to have force in member CB that we'll need to solve for. Let's see what else is going on. We have our distributed load, which I like to kind of draw them with like a dashed line, but then replace it with what it's actually equal to. So at the middle of the rectangle, we need to apply 75 pounds per foot, and it acts over a total of, it looks like 4 feet. Multiply that out and you get 300 pounds downward. And then over here, we've got a 150-pound force at our 30-degree angle. And what have I forgotten? Oh, I also removed a pin at A. So I only removed two things in drawing this. I removed the two-force member, replaced it with a force oriented along the two-force member, and then I removed the pin at A. So it's just a regular old pin. We're going to have an AX and an AY that we need to solve for. And as far as that bar is concerned, all of those blue things I drew on there are all external forces. But I need to do this step because I have to solve for AX, AY, and the force in CB before I start breaking things apart. So you guys remember how to do this from statics, I hope, but I'll show you again in case you've forgotten. I like to sum moments first when I've got a location with two unknown forces, because if I sum moments about point A, I'll be able to solve for FCB with just one equation. So let's sum moments about point A. They have to equal 0. Pick a sign convention like counterclockwise being positive. This is a sign convention for purposes of summing all of the forces on a diagram. So this is not the same as the sign convention I talked about up here for internal loads. Internal loads are kind of different. We can't call right positive or left positive because that normal force acts to the right on one object and to the left on the other side of the cut. And so we simply call these internal forces like that a positive because it's causing tension. In this case, though, now we're actually summing moments, and we need to make sure that all of the counterclockwise and clockwise moments about point A add up to 0. So what do we have? Oh, I need to find the orientation of FCB. I know it's going to cause a moment. If you look at the triangle, it looks like it's 4 on the vertical side, 3 on the horizontal side. So it's a 3, 4, 5 triangle. Let me actually draw it on there. It is a 3, 4, 5 triangle. So to get the moment, it'll just be the vertical component that causes a moment with a perpendicular distance away of 3 feet. So the vertical component will be 4/5 of FCB, and the distance away is 3 feet. The horizontal component, line of action, is directed right at point A, so it causes no moment. And this one is going to be counterclockwise, so it's positive. The 300 pounds, though, is going to cause a clockwise moment, so it will be minus 300 pounds. And it looks like it is, how far away is it? This whole thing was 4 feet wide, so the middle of the rectangle would be 2 feet over. From A, we'll go 1, 2, 3, 4, 5. So 5 gets you to the middle of the distributed load rectangle times 5 feet. And finally, the 150-pound force. Well, I need to break that up into its vertical component. That'll be 150 cosine 30 because it's adjacent to the 30. And the horizontal component would be acting right here. That is lined right up with point A. So I don't need to worry about the horizontal, just the vertical. And it will also cause a clockwise moment. So we're going to have minus 150 pounds times the cosine of 30 degrees. And it should be 7 feet away, equals 0. we can solve for FCB, comes out to be 1,003.89 pounds. Now, I would not leave a final answer that way. That's way too many significant figures, but I want to keep that number for when I use it later on so I don't accumulate much rounding error. Now that I found that, I can sum forces in the X and Y direction to get AX and AY. So summing forces in the X direction, again, I need all the forces to the right on this diagram and the ones on the left to balance. So I pick just right for positive. I will have AX to the right minus the 3/5 of FCB to the left, and then plus 150 pounds sine of 30 will give me the X component of that 150 pounds. It all adds up to 0. Solving, we get that AX is 527.33 pounds. And if I add the forces in the Y direction, they also have to come to 0. So AY plus 4/5 FCB minus the 300 pounds from the distributed load minus 150 pounds times cosine of 30 degrees equals 0. And I get AY is minus 373 pounds. Minus just means I guessed the wrong direction when I drew it on my diagram. It actually has to act downward. Okay, this was our first step, the whole free body diagram. I guess then our second step was equilibrium equations. We needed to do these because we need the reaction forces at A and the force in the two force member in order to do the next steps. So now it's asked us to find the internal forces at D, E, G, and F. We don't have to do them in that order though. I want to do F first because it's really easy. Remember, CB is just a two force member. So we just need to cut open this member at point F and draw a little free body diagram. Say we cut it at F. You can keep either side you want. There's my cut. It is a two force member whose force is FCB. Oh wait, why did I draw FCB downward? It was upward on this diagram. Well, remember, this goes back to your good frames and machines practice from statics, is when you're drawing point, I think that's point B on the diagram. Yep, when you're drawing point B on this, if you draw FCB up and to the left, when you draw point B on the other part, FCB has to be equal and opposite. That's Newton's third law, that this guy and this guy have to be an equal and opposite pair. So now at our cut, I want to draw on here my internal forces. The normal force doesn't act in a horizontal or vertical direction, it acts perpendicular to the surface. We're also going to have a shear force. Now, which way should we draw the shear force? I'm thinking of this as it's this part, but it's been rotated. So my normal force is going out and away. My shear force should actually be going up, and then my bending moment should be clockwise. So my shear force is going to go up and my bending moment MF is going to be clockwise like that. Now, let's see what's going to happen if we actually start summing things. If we sum forces in this perpendicular to the bar direction, we get that VF, oh, that's just equal to 0. And if we were to go in some moments about the cut, can you see that the normal force at F, FCB, and VF, they all go right through that point. So our moment is also going to be 0 for this. This should not be a surprise. It's a two force member. So all we're going to get is that NF is equal to FCB, which is that 1,004 pounds. And it's in tension because it was positive. You don't really need the free body diagram to figure that out if it's a two force member. Next, we need to cut open at D, E, or G. My suggestion is only cut open at one place. Don't cut open at multiple places. And when you do your cut, keep the easier side that has less stuff going on. If I cut it here and keep everything over here, I've got a ton of stuff to include in my equation. But if I keep stuff over here, it's a whole lot simpler. So let's do the cut at D. Here is my cut. There is the rest of the part to the left. At A, we found out we were going to end up with, to the right, 527.33 pounds. And AY, I guessed it was upward. It came out negative, which means it actually acts downward. I'm just going to draw it on here as a downward 373 pounds now that I know the direction it acts. And then at the cut, you always draw a normal force, guessing that it's in tension. And on this side of a cut, you draw the shear force downward and the bending moment counterclockwise. And let me put subscripts D on all of these because we are finding the internal loads at point D. Okay, now I have a great free body diagram with 3 unknowns on it. So I'm going to need to use 3 equations to solve. If we sum forces in the X, we need to pick a sign convention such as right positive because these guys are internal forces that we find by cutting open the part. But once we draw them on a free body diagram and we go to sum forces, do our equilibrium process, we think of them as basically external forces on this little chopped open piece. So when we sum, we just need to add up everything equal to 0. So doing that, we get 527.33 pounds plus ND equals 0. So ND comes out to be minus 527 pounds, rounding it. And what that negative means is compression. And that could be really important, right? We're in a class called Mechanics of Materials here. We want to know if something's going to break or not. And there are some materials that break a whole lot sooner in tension versus compression. So knowing not just how big the force is, but also whether it's tension or compression does matter. The summation of forces in the y direction next. I've got minus 373 pounds minus the shear force at point D equals 0. Solving, we get the shear force at D is also negative, comes out to be minus 373 pounds. That negative simply means, did it follow the positive or the negative sign convention? And finally, we need to sum moments. My favorite place to sum moments is about the cut. And the reason for that is if I have messed up my shear force, well, when I sum moments about the cut, my shear force doesn't cause a moment. And so it won't propagate the error to yet another number. So I sum moments about the cut. In doing so, you'll notice that the 527, this AX goes right through that middle of that cut face. So the only thing that's going to cause a moment is the 373 times how far it is away and MD that we're trying to solve for. So we're going to end up with MD plus 373 pounds times that distance. Oh, the distance is 1 foot. 1 foot equals 0. So MD is also going to come out to be negative. It comes out to be minus 373 pound-feet. And the minus will have implications for which way is it going to bend, up or down. For now, we just need to figure out the number and the sign. We're done with 2 of them. Let's do the third place. We're going to cut at E. And this is one where I don't know that one is easier than the other. E is sitting right about here. So you're going to be cutting through there. I decided to keep everything to the right because then I didn't have to deal with the 2 force member or point A, but you're still gonna have to deal with some distributed load and this 150 pounds. So I cut at E and kept everything to the right. So here's my cut. There is the bar to the right, and I have the downward 150 pounds. And now here is the point that's really important with distributed loads. Only keep the part of the distributed load that actually acts over your cut open thing. So you remember how back here, the distributed load acted over all 4 feet. And so when we found and replaced it with an equivalent force on our diagram of the whole thing, we multiplied the 75 by 4 feet. We got 300 pounds and we stuck it right there 2 feet from the end. But when we cut it open at point E, we can't include this part of the distributed load because that's not acting on this part of the thing. So we need to only include the part of the distributed load that acts on the actual piece we're keeping. So we're going to need to recalculate the magnitude and the location as well. I'm going to end up with a point force whose magnitude is 75 pounds per foot, but it's not multiplied by 4 feet this time, it's multiplied by 3 feet. And it comes out to be 225 pounds. And if you want to track its location, since the whole thing was 3 feet, it's going to be 1.5 feet over. Those are the blue external loads acting on this chopped off piece. Now at my cut, I'm going to draw the normal force at E out and away from the face. And on this side of the cut, VE would go up and the moment at E would need to be clockwise. If you ever can't remember that, go back to your sign convention and see, oh, my cut's on the left end, so V needs to go up. It is something to either memorize or keep this sign convention handy. We've got everything on our diagram. Next step is equilibrium equations. I need to sum forces in the x direction. Doing that, I've got to the left NE and to the right 150 pounds times the sine of 30 degrees. That all has to equal 0. So the normal force at E actually comes out to be positive 75 pounds. Positive means it's in tension. Let's sum forces in the y. Doing that, we get VE minus the distributed load, 225 pounds, minus 150 pounds times the cosine of 30 equals 0. So VE comes out to also be positive 355 pounds. And finally, we need to sum moments. Like I told you, I like to sum moments about the cut. Doing that, I guess counterclockwise positive, but my internal moment, ME, is actually clockwise. So it's got to go on my equation as minus ME. Also clockwise would be that 225 pounds from the distributed load, which effectively acts 1.5 feet away from the cut. Finally, I'll have also minus 150 pounds times cosine of 30, and that one acts 3 feet away from the cut. All adds up to 0, so ME is going to be negative again. It's going to be minus 727 foot pounds. Let's cut it open once more at point G. G is just the last little 1 foot. So I'm definitely going to keep everything to the right because it's shorter and simpler. So keeping everything to the right of point G, I've got just a little bit of distributed load. And then I've got the 150 pounds at 30 degrees again. And how big is that force going to be this time? It's going to be 75 pounds per foot times just 1 foot, or a total of 75 pounds. And where's it going to act? Is at the middle of our 1 foot length. So we've got 0.5 feet and 0.5 feet. And then at our cut face, again, we're going to have the normal force at G, the shear force at G, and the bending moment at G. Every time you've got a free body diagram, it's because you're going to write equilibrium equations next. So let's do it. Sum of the forces in the X is 0. We've got minus NG plus 150 pounds sine 30 equals 0. So NG is also 75 pounds. Then if we sum forces in the Y, picking an overall summation sign convention, we've got VG minus 150 cosine of 30 and minus our 75 pounds equals 0. So VG comes out to be 205 pounds. And it's positive. If I sum moments about the cut, also has to be 0. I've got minus mg minus 75 pounds times 0.5 feet minus 150 cosine 30 times just 1 foot away from point G equals 0. And mg is also negative, minus 167 feet pounds or pound feet. All right, that was a lot of work. It was a lot of free body diagrams and it was a lot of equilibrium equations. First step, always draw whatever whole free body diagram you need to get your reaction forces, in this case AX and AY, and the force in the two force member, and you need to do the equilibrium equations to solve for all of those. Once you've done that, you can start cutting things open. And every time you take a cut, you keep everything to one side or the other of the cut, you draw a free body diagram, and you solve for your unknown internal loads. Here's another cut, solve for internal loads using equilibrium equations. Here's another cut, solve for internal loads using equilibrium equations. And our last cut, free body diagram, and then solve for the internal loads using equilibrium equations. Why do we care? It's a really great question. Why do we care? The reason we care is if you want to determine if something is going to break or not, you need the internal loads to tell you, not the external loads. It's because it turns out the bending moment's bigger here than it is here. So that means it is more likely to break here than it is there. So we need to be able to cut parts open and find out how big are the internal loads and where are they biggest, so we can figure out if our part's going to fail. So that's why we care. And I'm going to stop this video here. Hopefully that gives you a good introduction to finding internal forces beyond just the trusses that you did back in statics.